Good morning, everybody. Thanks for the introduction, and also thanks to the organizers of the Sensors Conference inviting us to present recent results from our team on tactile sensor systems. Okay. Now, I have structured my talk as follows. After a brief introduction on tactile sensor systems, I will introduce or discuss sensor components, sensing elements that can be used in these tactile sensor systems, in particular in CMOS tactile sensor systems. I will introduce and detail then our 3D force sensor system, as well as a smart tooth that is used in the training of orthodontists. And finally, I will conclude. As you know, tactile sensor systems have a broad variety of potential applications, and these are just a small number of examples that you find in literature. We have them in robotics and prosthetics, where it is necessary to not only measure normal forces, but also shear forces, so that you can decide whether an object is gliding through your fingers. And this can be done with systems as integrated here in this robotic hand. We find them in medicine, and one example was shown this morning by the plenary presentation of Bob Pierce. This is a pressure sensor, but we also have them in small miniaturized surgery tools that give a feedback to the surgeon what kind of tissue he or she might cut through. But we also have them in something that is highly related to our smart tooth, namely in smart brackets. On the other hand, in consumer electronics, we have fingerprint sensors, and an example is here given by the group of Professor Tactile, combining membranes with CMOS circuitry, but also joysticks, or the need for small tactile sensors, mainly 3D force sensors for metrology of microcomponents, and that's another topic that I will talk about. Now, if you look at these systems, and in particular the system concepts, we can distinguish either the hybrid integration of a circuitry, and again an example that we have seen on Monday in our plenary session by the group of Isashi, where we have the CMOS circuitry combined with a dedicated sensing element, mainly in this case a deflectable membrane. Both are assembled in a hybrid way, and you can optimize either the circuitry or the sensing element, and then you have to bring them together. But this is most often accompanied by an increased fabrication and assembly effort that you have to take care of, but of course with advantages in, let's say, optimizing the inbuilt components. But, and this is maybe a potential drawback, that dependent on the actual application, you might affect sensitivity and also noise performance. On the other hand, looking at the direct integration of CMOS circuitry and the sensing elements, we might end up with highly miniaturized devices, as for example here in this situation. This is a penetrating neural probe that is inserted into the cortex, and it contains an array of force, or better to say stress sensing elements, that allow us to extract the mechanical interaction between the probe itself and the surrounding tissue, and this will allow us improving the implantation, but also to see what are really the forces acting during a long-term application. Nonetheless, the direct integration of CMOS circuitry and sensing elements allows us to improve signal-to-noise ratio, and if we apply additionally dedicated MEMS processes, we might further improve the sensitivity by integrating membrane or beam structures. This is the system concept. Now let's have a look at typical stress sensing elements that are found, not exclusively, but most often that are found with CMOS-based tactile sensor systems, namely capacitive sensing, where people designed and realized membranes through sacrificial layer technologies, either from the front side or the back side of our wafers. And I think a really smart example is given here, using the CMOS metal layers as masking layers, but also as sacrificial layers. This is an example by the group of Professor Wei Lung Fang at the Tsinghua University in Taiwan. What they do is that they pattern the topmost passivation layers and then etch through the multiple metal and dielectric layers to generate suspended membranes comprising an electrode. Again, as we combine the electronics together with the sensing elements, we can reduce the parasitics, can improve the noise performance. But of course, looking at, let's say, the capacitive sensing elements, if you make the capacitance too small, of course, you get really problems in view of noise, although, let's say, the power consumption of these devices is highly beneficial. Now, what can also be done, and this is also illustrated in this example by Liu et al., is that they can effectively modify the stiffness of their system by injecting a polymer of appropriate stiffness into the gap between the two electrodes, and thus increasing the range of applications because you modify, let's say, the overall stiffness of the system. Now, what we are mainly working on in our group is that we implement piezoresistive elements, namely the change of resistivity of silicon upon application of mechanical stress. This equation describes what happens when you have a resistor in a 100 substrate aligned under an angle theta with respect to the 100 directions of silicon. And we clearly see that this is dependent on the normal stress, but also the shear stress. The in-plane shear stress is here, and the respective piezoresistive coefficients, pi 1, and so on. And these coefficients are dependent on the type of doping, either N or P dope, but also on the concentration of the dopant. Now, this effect can be exploited in implanted resistors, but also in the inversion layer in field effect transistors, and we call them the piezo FETs in our team, and I guess anywhere else as well. Now, these systems are then used as Wheatstone bridges, and this here is an example of a FET-based Wheatstone bridge, where we see 4 contacts and the respective contacts to the gate electrode. On the other hand, we can also realize 4-terminal devices, and here on the right-hand side, this example shows an implanted N-well resistor. In this case, it's an N-well resistor used to monitor in-plane stress. Now, what can be done with these devices as well is, of course, that we can, let's say, tailor them in a sense that we either use NMOS or PMOS devices. We might use them as a 4-terminal device, or if we just leave a hole in the gate electrode, we would generate just the inversion layer here underneath the gate. And in that sense, we realize something that looks pretty like a Wheatstone bridge, and it behaves like a Wheatstone bridge with an improved sensitivity compared to these devices without hole. These NMOS and PMOS piezo FETs, they have a fairly good sensitivity on the order of 1.5 millivolts per megapascal when we apply drain source voltage of 4 volts. And on the other hand, if we are looking on the PMOS devices, we get a sensitivity of minus 1 millivolt per megapascal. PMOS sensors are then used to monitor the difference in the normal stress components, whereas the NMOS devices are dedicated for shear stress, for in-plane shear stress. These sensitivities clearly indicate that we can have a sub-megapascal resolution with these devices, and more important, looking at the linearity of these effects, we see that we can cover a broad range or a wide measurement range with these devices, from a few megapascal or less than a megapascal up to several hundred megapascal. Moreover, these effects are temperature compensated as long as we do not take into account the temperature dependence of piezoresistive effects. Now, these are in-plane stress components. If you want to monitor out-of-plane stress in the wafers or in the silicon sensors as well, you have to come up with new ideas. And one new idea here has been developed in our group, where we use, again, a P substrate, and we generate a circular contact CR and the central contact CC, and we inject the current between these two contacts. The contacts by themselves are separated by a N-well that drives the current deep into the structure, and in that sense we can monitor at the end, using these pseudo-Hall contacts, we can monitor the out-of-plane shear stress. Here in this case, it's the out-of-plane shear stress x prime, sigma x prime z prime. And if you have contacts that are arranged orthogonally, so in this direction, you would monitor the shear stress sigma y prime and z. We implemented these stress sensing components in two applications that I want to detail in the coming 20 minutes or less. First of all, a 3D force sensor. In this case, our main application is driven towards the coordinate measurement of microcomponents. And what you see here are three examples where deflectable structures are used. Here in this case, it's a membrane with a tactile pin here down. These are several cantilevers that are used with a tactile pin as well. And here in this example, we use a cross structure that is suspended through thin membrane hinges, and again, a tactile pin. Now, the disadvantage of all these three components is that you are somehow limited in the number of piezoresistors that you can integrate, or better to say, the number of leads that you can bring out if these are purely passive components, as it is here in this case. So, question, or the answer is quite clear. What if we integrate CMOS circuitry? Can we get rid of all these problems? And I would say yes, we can do. So we can minimize the large number of wires. We can integrate more piezoresistors in different positions on these membranes, and ultimately gain more information on what is going on in these specific devices. Now, based on this design here, which is a sensor that we fabricate for its size for their F25 coordinate measurement system, we developed a CMOS-based 3D force sensor. And this system again contains this cross structure with the thin membrane hinges suspending this cross structure inside frame. And we integrated on all of these 8 membranes 3 piezoresistive stress sensing elements. That's part number 1. We integrated further 2 reference sensors just in the thicker cross arms that should not experience any stress at all. And then we combined that with a tactile pin. Now, these systems are deformed when we apply a force in either the Z direction or X and prime direction, and this deflection of the cross structure is characteristic not only to the direction of, or mainly to the direction of the force that we apply, and the amount of deflection, and thus the amount of mechanical stress in the membranes is related to the amplitude of the force that you apply. So you have to decide where to place piezoresistors, and if this is done in a clever way, you get an optimized sensing system. Now, our CMOS-based device comprises 32 PMOS stress sensing elements. So they monitor the difference of the normal stress components. We combine them with an amplifier with a gain between 100 and 700. We have an AD converter. In our case, it's a successive approximation AD converter with a resolution of 8-bit. And everything is then combined with the digital logic, which is used to calculate the signals that we obtain, and also to communicate with the outside world through an I2C-like bus system. And this is how the device looks like. This is a typical CMOS chip with a size of 6.5 by 6.5 millimeters square. It comprises the electronics just here in the lower right corner. We don't need more space for that. We integrated relatively simple alignment structures that have been used for the post-CMOS processing. And what you see here, in a bit more detail, this is later on the position of the membrane hinges. So these are the outer membrane hinges, and here we have the inner membrane hinges. And as mentioned before, we have 3 piezoresistive field effect transistor elements integrated in the membrane, plus a reference sensor. And on the outer membranes, we did, just for curiosity and for testing, additional shear stress sensors. So these are the FETs here, and they are accessible through additional contact pads here at the rim of the wafer itself, but they haven't been used in those measurements that I will show you later on. Yeah, and this is a detail on the stress sensing elements without a non-conducting island in the center. Now the fabrication itself, as mentioned, is based on the CMOS process. So we use a standard CMOS process. We do it in a multi-project run with other partners, and then we do the post-CMOS processing. Part of the wafer, or part of the wafers are then processed, mainly grinding to obtain a total silicon thickness of 400 microns, a masking layer deposition and patterning on the backside. So this is the green area here, and dual-sided deep reactive ion etching to generate trenches from the backside that stop at the depth so that we obtain membranes with a thickness of 20 microns, and to release the structure when we open it from the front side to have this truss structure. The central hole here is simply integrated to facilitate the assembly of a tactile pin. You clearly know where the pin has to go to, and it's centered. Now, using these systems, of course, we had to calibrate them, and we had to look at the sensitivity of these systems. So we applied, okay, and this should be a delta set here. At least this was on my computer. So we applied the displacements of the probing sphere up to 6 micrometers in the same direction, in the y direction. We monitored the signal of our AD converter. So what you see here is the least significant bits that is obtained from the system itself. Now what we see is independent on whether we use the inner and outer membranes, the sensitivity for forces in the Z direction is around 11.6 least significant bits per micrometer in the Z direction, whereas if we apply a displacement in the X and Y directions, we see that the inner membranes, so this is the signal for the inner membranes, the inner membranes have to be preferred in this case to obtain a sensitivity of 4.5 least significant bits per micrometer. And we used that and had a closer look at what's going on. So if we applied displacements on the order of, or as precise as possible, of 200 micrometers, and this is shown here. So we see the increase of the set signal when we step in 200 nanometer steps. The same here on this side. This is the result for the Y direction, whereas the Z direction doesn't show anything. The same is true here on this side. From these numbers, we conclude that the resolution in the Z direction of 15 nanometers is reasonable. In the XY directions, we are slightly less good and achieve here 50 nanometers only. So this is the 3D force sensor system. Now coming to the smart tooth. The smart tooth is a system that we want to realize and generate to have a training system for orthodontists. Why is that necessary? Now, if you look at these images, and I guess some of you have experienced these brackets, either by yourself or you have to pay them for your kids. And what you see here is that they are fixed on the teeth, and you have a wire that is fixed to these brackets, and by deforming the wire, you can apply forces and torque to individual teeth. Why should we need a training system? Now, if we look at the typical forces that have to be applied so that you see an effect of these brackets, is we need forces around plus minus 1.5 newtons, and we need a moment applied to the tooth to, let's say, deal with malocclusions and tooth malpositions of 1.5 Newton centimeters. Now the effect is if the numbers are, if the forces and moments are too low that you apply, there will be no effect. The teeth tell you what's going on. I don't move at all. If you apply forces which are too high, you might see root resorption or an irreversible loss of dental hard tissue. And this is, of course, something you have to definitely avoid unless you like to have kids with missing teeth. So that's not good. So we have to train the orthodontist, and a system that might be used could look like the following illustration. So assume you have an artificial crown, you fix one of these brackets, and inside the bracket you have this wire. Deforming the wire will generate forces and torque. So can we measure that? We say yes, that's possible by using that smart tooth sensor module that is mounted underneath this artificial crown. Everything is connected by a polyimide wire You might use thicker wires as well, but we use here 10 micron thick wire just to have everything as flexible as possible. It allows detecting loads in the X, Y, and Z direction. And if you combine several of these components into an artificial dentition, you will be able to train the orthodontist, because now they can train with that very specific device, having a feedback, which force is applied, which torque is, or which moment is applied. Now, our system contains of mainly 4 components. 2 pins. In between these pins we have the CMOS chip. And the CMOS chip by itself is then, oops, okay, this movie is also not working. So the CMOS chip is then connected to a cable. So these are the 4 components. Now if we apply a force in the Z direction, we see a very characteristic stress distribution inside this chip. And this is true for the shear stress component, the in-plane shear stress component, and the 2 out-of-plane shear stress components, Y prime, Z prime, and X prime, Z prime. And then if we use other force components, Fx and Fy, we see very characteristic stress distributions in the chip. And if you're able to monitor these stress distributions by applying sensing elements at strategic positions, you will be able to distinguish these different force components. Now, this is done in our case with CMOS chip, again realized in an 0.6 micron CMOS technology. Size is 2 by 2.5 millimeters. We have 14 piezo FETs, in this case P-type piezo FETs, that monitor the difference of normal stress components, and their location is indicated by the circle, so they're mainly at the rim plus 2 more central. We have 10 NFETs that monitor the in-plane shear stress component, indicated by the squares here, the corners, so strategic positions where we integrate them. And finally, we have 8 vertical shear stress sensing elements, and they monitor the out-of-plane shear stress component, either X prime, Z prime, or Y prime, Z prime. All in all, we have additional components as before, and as we have seen with the 3D force sensor system, so amplifiers, the AD conversion, and the sensor biasing. We have a multiplexer to guide current in different directions through our stress sensing elements, and here the digital logic for the data processing and the I2C like circuitry. The assembly of these devices is relatively straightforward, although we had to perform a couple of optimization processes, in particular in view of the stability of the device. Now what we use these days is that we take the chips, we have gold bumps on the chip, and we flip chip bond this polyimide cable directly onto the chip. This is then secured with an additional EPO-TAC adhesive that strongly adheres the cable to the chip itself. Then we mount pins and chip together with the cable together, so that the chip by itself is sandwiched in pin 1 and pin 2. And this is how the system looks like at the end. A length of roughly 12 millimeters, but most of that is used just to mount everything inside the artificial crown or anything at the bottom where you have to fix it. The cable by itself is roughly 50 millimeters long. You might make it longer or shorter dependent on the actual design of this artificial dentition. These systems are then calibrated with a custom-made setup, and what you see here is a frame with multiple stages that allow you to tackle here a load arm, and this load arm is connected to your smart tooth system. What you also have is here a reference sensor that is capable to monitor forces and the moments. So this is the reference sensor, and here is the smart tooth sensor module. Doing that, we perform these calibration measurements, and typically this is done in a way that we apply a certain number of different load cases, and we measure the forces and moments provided by the reference sensor. We of course measure the sensor signals, and in our case 32 sensor signals per load case, and then everything is fed into a calibration matrix, so namely the reference sensor signal, chip sensor signals, and then the combination of the reference sensor and the sensor signals of the smart tooth and the load cases. And our calibration matrix is mainly the pseudo-inverse of this matrix T. By doing so, we apply a certain set of load cases. And what you see here is, as the solid line, this is what we obtain from our reference sensor. And having already a calibration matrix, we calculated the respective signals of the sensor module, and I would say they fit quite well. So that's a proof of principle, both for forces and the moments being applied to this sensing module. And I think this is even more clear here in this picture, where we compare the forces and moments obtained by the reference sensor with those obtained by the smart tooth sensor module. What you clearly see is that the forces Fx and Fy are perfectly matched with a low standard deviation below 0.25 newtons. However, in the z direction, we see a decrease. We see an increased standard deviation. This is mainly driven by the reduced sensitivity of the out-of-plane stress sensing element. The same here is true for the moment component My. Here again, the standard deviation is slightly increased to the components Mx and Mz. And again, driven by the reduced sensitivity of this shear stress, out-of-plane shear stress component. Yeah, let me conclude. I hope I could present a 3D force sensor system that is used for the metrology of microcomponents. I would say we have a reasonably good resolution of 50 nanometers or better. We have minimal contact forces that are necessary for microcomponents to be monitored. On the other hand, the smart tooth system, I think this is a tool that will go into the orthodontics universities, but also and the training of the students this way. So this will be a tool where they train and see that the treatment is optimized, but they can also use it to evaluate new treatment. What I think is very important, and I haven't shown the data on that, but this is the summary. These systems are stable for forces up to 60 Newton and moments of 10 Newton centimeter. Going back to the required forces, that's way beyond what we have to apply. And I think with all these Piezo stress sensing elements, these are examples of applications, but I think we can find new ways of integrating these stress sensing elements. I think most important here with the piezo FETs, they are very small, they are 10 by 10 microns squared, so you get a really good lateral resolution. In that sense, thanks for your attention and thanks for funding and Pascal Gischke for characterization of our piezo FETs. Thank you.